Okay. I hope it's okay now.
It's okay now, sir.
Okay, good. Yeah, sorry. There's a technical problem. I don't know why it stopped microphone. Okay.
Okay.
Okay, good. I think that you got the correct answer, I think. And let me check again.
Hello,
Okay,
sir.
so everyone, yeah? Any problem?
No, sir. No, sir.
Oh, okay. So this is a solution I got in my slides. So I think that all of you understand this problem because we see that the highest orders of S is n equal to 3. And we find that, okay, you can represent this system by this form. Okay, and you are correct. Any questions so far, everyone?
No, sir.
Okay, good. Now we can move on with this. Okay, in this example, you try with this one more times and see that in this case, Bn here different from 0. And in this case, we got Bn equal 2. And An in this case equal 1. Okay, so this is still proper, not strictly proper, because the highest orders of the numerators equal to highest orders of the denominator. But now we have to find the controllable canonical form for this system and see what difference with compared to the previous case. Okay, now let's do it. Everyone, try with this example. You finished?
Not yet, sir. Just wait.
Okay, okay, no problem.
Sir, I just put it on Zalo group. Can you check it?
Okay, okay. Yeah, I check it. I think it's correct. What about the other? Did you find a solution yourself?
So I got a 7, sir.
Okay. What solution? Okay, you can find your friend's solution, and if you have any idea, other ideas, just tell us. Or do you have any questions about it? Okay, do you have any questions? No?
No, sir.
Okay, good. If, so I think that this is the correct answer. So this is my solution, and also I do it myself. So maybe I got also mistake. But I check. I think that we have the same results, and Uh, in this case, see that we have the highest exponential of n a 3. So n equal to 3, and we specify a3 equal to 1, a2 4, a1 is 11, a not is 9. So we have 9, okay, 11, and 4. Okay, so we have 0, a1, and a2. The maximum is a2 because we have n minus 1. And in this case, we see that Bn, in this case, Bn is B3 and equal to 2. So we follow this form and see that in this case, B naught is not different from 0. And also this different from 0, different from 0. So we will see that we got C in this form and also D. We got also D. Okay. So that's the reason why for the answer, you're correct because we have here this C, configurable canonical form, and X plus D in this case, very simple, but it's still used. And in this case, we have D, canonical form equal to, okay, or this is matrix, but we have only one element. Okay. Okay. So here you have no questions, so we'll have a break, okay, for 5 or 10 minutes. Okay.
Okay, sir.
Yes, sir.
Okay. Okay.
Thì mẹ sao? Đây đang học. Ở bên quạt. Đây.
Chạy nhiều đi, vừa làm vừa học. Chúng ta chưa bật điện rồi. Đấy à? Thôi học viên lập phạm mới được cho nên phá hết đúng rồi. Ôi đang học thật.
Okay. Now I'm back. Are you still there? Okay, now we move on to the next form. We call this a observable canonical form. But actually, this form is almost the same as the previous one, but now we change. We transpose the matrix a little bit, so it looks like this. The observable canonical form, we see that we change. Yeah. Now, the row becomes the columns. This is matrix transpose. But we have the different form of B and C. You see, they have different things. For the matrix A, we got the first round here, all zero except the last one. Okay, the last component of the first round is minus A naught, minus A1 up to minus n minus 1. And the B is now is B similar or same for C in the controllable canonical form. Okay, actually, but this is a T transpose. Okay, and here you see that this is a B of controllable canonical form transpose. Okay, and here you see this is a transpose. Okay, it looks like this, but D is same. So if we represent a system in this form, we'll have another canonical form, and we call this observable. This observable canonical form. Okay. So this is second way we can represent the system in space equations. Okay, and again, it's quite similar to the previous one, except that the matrix ABC now transposed and D give the same. Okay, so this we got the relationship between observable and controllable canonical form. Okay, so I think that this is another way, but everything we all know. So if we consider again example 3.1, okay, here, see, we got this, the system in transfer function form like this, and we got this is the controllable canonical form like this. So we only made a similar way, apply the formula, but we make change, okay, a little bit. So we got this is observable canonical form is quite easy. X1 dot, X2 dot becomes, okay, we got 0, 1, and here we got -2, -3, and here we got X1, X2, and here we got this transpose 3, 1, okay, use, and we got the output will be 0, 1, X1, X2, and plus BU. Bn, but Bn is 0. Okay? So we just take a transpose. Okay, then we got the solution for observable canonical form. Okay, so this is the way we represent the system in observable canonical form. Okay. So how about it? How about the second example? Okay. You can find this easily. Okay. But okay, let's practice a little bit. Write yourself the observable form of this. Of course, this is only a technical problem, but practice yourself to be remembered. How can we make the transpose matrix? It easy?
Yes, sir. Easy.
Okay, easy. It's easy. Okay, just make us. It look like this. We got x dot equal. Okay, we take 0, 0, 9. Okay, and here we got 1, 0, 11, and here we got 0, 1, -4. Okay, x plus, here we got 17, 5, 6, use, and here we got y we got 0, 0, 1, x. Okay, that's all. Okay, just this is a observable canonical form. Okay, the transpose of the computable canonical form. Okay, so now we move to the next form. Okay, this is sometimes when we show the space equation, we need to calculate the transition matrix. Fine, if you still remember, we have transition matrix E, AT. Okay, so if you found this, then we can easily show problem. Okay, so we got another form. If you can represent the system in the diagonal canonical form, then we can find this easily. Okay, so we will learn how to represent a system in the diagonal canonical form. And first, we have a look what is this. Okay, the diagonal canonical form is the space model in which the pole and transfer function are rearranged in diagonally in A matrix. Okay, now we assume that this is a system like this, and we can find the poles of this. I hope you still remember the solution of the numerator we call 0. And here we call this a pole. The solution of the denominator equation or characteristic equation, or call this a pole. Okay. Now in the diagonal canonical form, we assume that we got all P1, P2 up to Pn here is distinct. Okay, meaning that we got P1, P2, and P up to Pn are different. Okay, we have no identical root or solution. Okay, and if we got some of them are identical, then we have another form. Okay, so I will show you later. But at the moment, we assume that all P1, P2 up to Pn are distinct. Okay, then if they're distinct, then we can rewrite the system by this form. Okay, so we will have the separate all of this into some fractional component like this. And the problem is that we have to find C1, C2, and 3n. Cn. Okay, how can we represent it like this? If you can find C1 up to Cn in this form, then we can represent the system in this form. And this form called diagonal canonical form is because all the elements in the main diagonal is minus P1 minus P2 up to minus Pn. Other elements are 0. So we will got the diagonal this matrix. Okay, the system matrix A in this form, and the matrix B like this, and all C1, C2 up to Cn in the C matrix, in the output matrix. And if we got Bn, this Bn will be this. Okay, so if we can find C1 up to Cn in previous form, then we can represent a system like this into a diagonal canonical form. Okay, and if you represent this, then we will easily find the solution of the state space equation. Okay. Here we got something to find C1, C2, and Cn. Okay. Now assume that we can represent it like this. This tricky proper system, tricky proper. And in case not, I will show you later. But we assume that we have no Bn, and we represent the system in this form. Ts equal to C1 over S plus P1 plus T2S plus P2, and so on, up to this. Okay, up to Cn. If we have to find C1, C2, and Cn, we have to remember that, okay, if this, in this case form, we have Ck a constant, and we call it residues, the residues at pole S equal to minus Pk. Okay, and we can find it by using this. Okay, you can find Pk by multiply both sides of above equation by S, this equation. Okay, by S plus Pk, small pk, and then let things S equal to minus pk. For example, now we have the previous equation is Bs over As. And now we multiply by S plus pk and see what happens. Okay, so we got, we assume that we represent As, Bs by this form. Okay, so we got, first we got C1 S plus P1 multiplied by this. Okay, C2 multiplied by this, and so on up to Ck. You see that we have Ck S plus Pk S plus Pk. Okay, and we do this up to the last one. We got Cn plus S Pn, and this is Pk. And now we let S equal to minus Pk. So see, and by this equation we can eliminate this and eliminate this. We got Ck. Okay, but for other elements or component, because S equal to minus Pk, so this is 0, this is 0, and also 0. All the other component of this will be 0 if we take S equal to minus Pk except Ck. Okay, so if we want to find C1, meaning that K equal to 1, we just multiply the previous equation with by S plus P1. 5P2, replace Pk here by P2. That's all. Then you can find all C1, C2 up to Cn. And then after that, you will find the diagonal canonical form. Okay? So this is a general equation to find Ck. Okay? Now look at the example. Okay, now you are given a system transfer function like this. And the question is, find the diagonal canonical form of the state space model. Okay, so we follow this previous one, and now we see that the transfer function of the system in here can be represented by this form. Okay, because we find the roots of this. We find the roots of S squared plus 3S plus 2 then we will find that we got S equals -1 and S equals -2. Okay, so we have two poles. The first pole is, okay, P equal 1 and P2 equal 2. Have two poles here. Okay, this is P1, this is P2. Okay, so we got this, then we can represent the system with the original one by this. Two components, C1, S plus P1 and C1, C2, S plus P2, like this. And you have to find C1 and C2. Okay. To find C1 or K equal to 1, we got C1, and C1 is S plus P1. P1 is 1. And multiply by this, the original one, and take S equal to minus P1. Okay. Then you see we eliminate this by this. Okay. Finally, we replace H here equal to P1 minus P1 or minus 1. So minus 1 here, we got -1 plus 3, we got 2. Okay, so we got this one. So we got -1 here plus 3, we got 2. Okay, so -1 plus 2, we got 1. So we actually it equal to 2 by 1 or 2. Okay. Similarly, for K equal 2, we got C2 here, and we take S plus P2, mean S plus 2, and multiply by this, the system transfer function. Then we eliminate this and eliminate this. When we got S plus 3 here, okay, we got S plus 3 divided by S plus 1. And we we replace S by -2. So we got -2 here, then we got -2 plus 3, we got 1. And -2 plus 1, we got -1. So finally, we got this, S -1. Okay, so we find that C1 equal to and C2 equal to 1. So we represent the system by this form. This is a diagonal canonical form, because we got here is P1 minus P1, and here we have minus P2, and all this 1, and here we got C1 and C2. Okay, for C. Okay, that's all. This is for diagonal canonical form. The key problem is that we have to represent the system by this form. Okay, and if you can find C1 up to Cn, then we can easily find diagonal canonical form. Okay. Now, I think that we will have some practical exercise or practical example. Okay. Now you are given the system function like this. Find the diagonal canonical form space space model. Now, do it yourself, please. Follow my example here. Okay, first write out this. Write out the problem first, and I will show you the slide that contain the equation to be applied to find the solution of this problem. Ts equal to S plus 2 divided by S squared, sorry, S cubed plus 11S squared plus 10S. Okay. And now you have to find the canonical form. By this form, you see, you have the A matrix with all the pole in the main diagonal with the minus sign. Okay, in the main diagonal. And for C matrix, we will C1, C2, up to Cn. Okay. And Bn in this case 0. And to find any CK, you can follow this equation or in compound form in this. Okay, now do yourself, everyone. When you finish or if you have any problem, just let me know.
Sir, I just send it on the Zalo, sir.
Okay, okay. I think that you have to check then because you see that you've got the denominators, the order is 3, not 2.
Okay, sir.
Order is 3.
Okay, I forgot this. Sorry.
Okay, and also the pole in 1 and 10s, not 1 and minus 10.
Sir, just put it again.
Yeah.
Hope it's correct.
Okay. Okay. I hope. Okay. So we got P1 is 1, P2 is 10, and P3 is 0. Okay. We have C1. Now I have to separate this problem into 3 cases. And first is C1 divided by S plus 1, C2 S plus 10 S3 divided by S. Okay. So C1 is just multiply the system by S1 S plus 1. So we eliminate S plus 1. So we got S plus 1 eliminated. So we got S plus 2 and divided by S plus 10 S. What we got? Now you replace S equal minus 1 here, and we got minus 1. Okay, so here we got 1 minus 1, so we have 9 and minus 1. Okay, so 1, 9. Okay. Okay, in the second one, it's still similar. We multiply as 10, so we eliminate S plus 10 and put 10 minus 10, and we got minus H divided by 90, and we got 4 divided by 45. Okay, good. And the last one is this. Okay. Okay, I hope it's correct. Now check with other. Okay, minus 1 minus 5, 1 minus 9, 4, 45. It's almost the same. Okay. We have, okay, it's interesting because we rearrange C1, C2, and C3. So, okay, so I didn't see C1 in this game, 5 minus 24. Okay. And how about use in the how about D? We got D or not? So for the second solution, okay, for cells, let's check with the second solution, please. So in the first solution, we got here is minus 1, minus 10 is 0. And here we got 0, minus 1, minus 10. Okay. And this the interesting is that we have the same system with have at least 2 answers. Okay. And I think that this is a minus 4 divided by 45.
Yes, sir.
It's the same, but we have no D. Okay, no D part. Okay, so it's good. You know how to solve this problem. But remember, when we have the numerator have where you get this? In this case, see that the numerator here has the order smaller than denominator, so we have no Bn. Okay, so we have no D. Okay, so no Bn or Bn equals 0, so we have D is 0. Okay, the D pass of O. Controllable canonical form, observable canonical form, even this. Okay, because you see that the zero form of this is Bn. Okay, but Bn here is 0, so we got no D. Okay, I think that all you are both correct. Okay. In my case, I got a low solution here, but I think that the first, you can see that if you separate the problem into, okay, we're going to look at the first one. We can represent TS like C1, 1 over S plus 1 plus C2, S plus 10 plus C3 divided by S plus 0. So we'll see that we got P1 is 1, P2 is 10, and P3 is 0. Okay, so we will see that we got a matrix in like this. Minus 1, okay, sorry, this 10, okay. Minus 10 is 0 here, and all other 0, okay. But if you represent the system like this, TS equal 1, sorry, S plus 2, S plus 2 divided by S plus 1, S plus, because in 0K, you can represent it this way. You have TS equal S plus 2, and you put S outside, and then you got S squared plus 11S plus 10. Okay, and it equal S plus 2 divided by S, okay, plus 0. If I would like to emphasize that we got a key, in this case is 0. So here inside we got S plus 1 and S plus 10. Okay, so we have 3 poles. Okay, 3 poles. And in this case, we will write this form and write this form. C1 divided by S plus 0 plus C2 divided by S plus 1 and C3 divided by S plus 10. Got a similar answer because we will see that S1 equal okay. In this case, you find that C1 equals 1/2 or 1/5. Okay, let me check the answer.
1/5.
On 1/5, sir.
Okay. The first here.
Yes,
C1.
1. The first coefficient.
This is 1
1
over
over 5.
5.
Yes.
Okay. Okay. And C2 A1
Minus 1 over 9.
minus 1. Okay. Good. 3
Minus 4 over 45.
minus 4. Okay. Good. But if you represent it this form, we got C1 is how much? Okay, is it 1?
Minus 1 over 9.
Yes. Okay, minus 4 over 45 and C3
Plus 1 over
1. Okay. So you see, I told you, even you've got one transfer function, you have many ways, okay, to represent it. Like you can use continuable canonical form, you can use observable canonical form or diagonal form, but even in diagonal form, you see that we can rearrange the state variable in different way, and we got different results. Because I've emphasized you from the beginning of the course, the state space equation is not unique. Okay, and another note here. Here we have some thing about in the K we got no. You have TS here, TS equal Bn Sn plus, and here we got An Sn plus. Even we got no An, or in other words, An 0, or even more like An minus 1 also 0, or in other words, the orders of the numerators is bigger than the orders of the denominators. Okay, sometimes it happens this way. Okay, we still represent TS like a polynomial in S even. Okay. It looks like this. You got here the orders of the numerators here is 3, but the order here is only 2. Okay. So how can we do that? How can we represent it in uh, the polynomial of S? Okay, as before, and you find C1 and C2 for this case. Okay, you will consider this after break. Okay, now I take break. Have any questions so far?
No, sir.
Okay, good. Okay, now let's take break.
Linh ơi, Trần Văn Linh, nghe thấy không? Linh ơi, alo, tao gửi cho mày cái link này, tìm nghiệm nhanh, tìm nghiệm po nhanh.
Okay, are you still there? Okay, so this is the notice about the K that we got, the orders of the numerators bigger than the orders of the denominators. Okay. So, for example, if you got this,
Sir,
you can see that this transfer function, sorry?
sir, can you share the screen again?
Okay, sorry. I didn't see this. Oops. Okay. So this is an example of this. Okay. You see my screen now?
Yes.
Yes, sir.
Yes, sir.
Okay. 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 Good. So this is an example. We got the orders of numerator is 3, but the order of the denominator is only 2. Okay. But actually, this transfer function can be represented by this form. You can take the division of, because we have the two algebraic polynomial, so we can easily take the division of the numerator by denominator, and we got this form. Okay. So when we got this form, you can only take the fractional part of this. Okay, and you see that in case you still need, I don't have this one. Okay, you still we have this one, so we can rewrite it this form: s plus 1 and c2 s plus 2, and we keep s plus 2 like this. So you can rewrite it in this form. Okay, so we need to find only C1 and C2. Okay, so assume that we got another form of this like this. Okay, so in this case, you see that we got here the orders of numerators is 4, and the orders of the denominator is just 2. Okay, now you have to represent it in this form. Okay, meaning that we have to take the numerators here divided by denominator and got this form first, and then find C1, C2 later. Okay, so practice. Okay, so this example, you have to practice this.
Sir.
Okay, now try yourself first.
Sir.
Yeah.
If after we divide it, then the numerator, the order of this is equal the same with the denominator. So what next? We divide again?
No, because this you can got see this when we got this remaining part. Okay, when you have to we have make a division, then this is the remaining part. Okay. Okay. So in case we only consider A when we cannot divide it anymore. Okay. So we want this form. Okay. In case that we got the orders of the numerator equal to the order of this, you still take another division in this case. Okay.
Yes, sir.
Okay. So just practice for this problem first, because this is just a remark. Because the problem is we have to know this and represent this system, but it's only in a very specific case when we consider some problem that maybe not exist in reality. But in theory, you have to take care all. Okay, but in reality, we have to know this, because this is not technical problem, it's scientific problem. Okay, maybe it's not never happened in the real system. I'm so sorry. This is S plus S. This is not S plus S two. This is S plus S. Sorry, S multiply S plus one, not plus two. Because if you go S two, so we will have not as we expect. Sorry, change this a little bit for me, please. Mm. Đấy. Nè, anh bảo em chứ ai bảo anh bảo với ai.
Ta không nghe được điện thoại, đừng có điều chúng ta gọi cho em.
Oh, finished?
I'm doing, sir. Please wait.
Okay, no problem. Just
Sir, I got stuck on this.
Yeah.
So how to do next?
Okay. Okay. So we got this one. Okay, no problem. Just wait for the other. How about the other? I think this is the correct answer. Okay.
I got the same answer, but the the D here is capital D here is equal to 1, right? So
No. Please wait. Okay, I'll check this. Okay. What? Can you show the solution? Okay, this is the same solution, I think. Okay. Yeah. So in this example, I didn't show you the form or diagonal form because we don't care much about it because I said we can still represent the transfer function and find how can we represent this as you got before. Oh, what is it? I need this. Okay, I don't have this. But the solution, I think you got the solution is correct. I think. Okay, because we got it look like if I if TS can be represented by this form equals S squared plus S plus 2 and how much you got here is plus 5 over S minus 3 S plus 1. Okay, because we before that we got S squared plus S plus 2 and here we got 2S plus 5. Remaining part is this, and here we got S plus 1. Okay, and then we represented this form. Okay, but as I said, this week we do not find the diagonal form because this system is not exist in reality because this is not proper representation, and I will come back to this later, okay, to explain why. But at the moment, I just show you that, okay, even the orders of numerators bigger than the orders of denominator, we still got C1 and C2 this way. But we did not give, I did not give you the form of solution of this. Okay, so keep this in mind. I will be back with this later. Okay. So we'll move to the next form, the last form, in case that it look like similar to the diagonal form. But in the diagonal form, we assume that all the root of the denominator are distinct. In case that we have some root is identical, then we cannot apply this the diagonal form anymore, but we have to consider another form, and this is the last form, the Jordan canonical form. Okay, so what is this? Okay, this is type of diagonal form, but we got some involves multiple repeated root or identical root. Okay, now we assume that if you look to this form of transfer function, and we got the P1 here is identical, meaning that we got s plus 1 multiply s plus 1 multiply s plus 1, and then we got 3 times like this, and then we got 3 identical root, and then we have 4, 5, and up to n. Okay, so in this case we have 3 identical root or solution. Okay, and then we can represent this system like this. Okay, and only if you consider only proper k, it's like this, have no bn. Okay, so in this case, we can represent the polynomial form like this, and we have here this p1 cube, and then p1 square, p1 have 3 c1 c1 repeated 3 times, and then we got c2. Okay, this is c3. C2, C3 up to Cn. Okay. So we can represent this is the system like this. And if you can represent the system like this, then we got the Jordan form. Okay, and the Jordan form is like this. We got here's all the repeated root, the first. Okay, and then we got the next, but repeated in this, you have to here, remember we get this. Element is not diagonal anymore, but we got some other elements like this. Okay. Then the last and the next block, this is the first block of the, this is the first block of the system matrix, and the next block here is diagonal, but the first here is not diagonal, and we have to represent it this form. And for C, then we have to represent C1, C2 up to Cn. Okay, because we have only n variables like this. Okay, so in this case, it's a special case of diagonal form, but in this equation we have system matrix consists of 2 blocks, and the first block is not diagonal, but the second block still diagonal with the distinct root. Okay.
And can you explain the P part of this form, sir?
What?
Can you explain the P, capital P part there, with U, with input?
Here? Can you
Below,
repeat?
sir.
I didn't.
below, sir. The matrix 0, 0 until 1. The
This
matrix
D matrix.
multiply with you. Yeah.
Yeah. Okay, so this is a the matrix. This is A and this is B. Okay, this B matrix. Okay, so okay, this could be 0 here. Okay. Oh no. Maybe I have to check this again because it could be 0 or 1 because this depends on the we got a list because we have to check how many x we got here. Okay, so this is x1, x2, x3, x4, up to xn. Okay, so it's like this. We got repeat of here, here, and we got here is the 2 up to 3 cn. Okay, so we have only 1, 2, 3 up to cn here. So this is a number of the input here should be consistent with this. Okay, so we have to check this in an example. Okay, I will try to find example like this. We will find this together. Okay, and to find the solution here. Because when I prepare this, I do not give an example. Okay, because we have to have no time to prepare this. So I assume that okay, like this. We assume that we got the transfer function. We check together. Ts equal to s plus 3 divided by s plus 1 square. And we'll take very simple example, s plus 2. This. Now, how can we find the solution for this? Now do it together. I have no example yet. I have to do myself, and you also do the self example and check the results together. Now do it, please, everyone.
Sir?
Yep.
One
My
K,
solution.
yeah, but 1K I found equal to infinity. Something like that.
No, you do not push the s plus 1, but we check with the s plus 1 square.
Just
Okay.
plus 1 square?
Yeah.
Only plus 1
So
square?
we multiply by s plus 1 square. Because if you multiply with s plus 1, you still have x plus 1, and you replace s by minus
Minus
1,
one.
you have infinity. Of course.
Yeah.
Yeah. Oops. Take times for this. Okay.
Sir, I don't know why, but I'm got stuck on this. I have no answer.
Okay. No answer. Okay. Can you show me?
You cannot because I just take a wrap. I have many.
Uh-huh. Okay. Okay.
So maybe Thầy Đức will show
Okay.
to you.
Okay. Okay. So in this case, I have no. I think this is not correct. But okay. I think that it should be something. Yeah, there's something. This still my see is my slide.
No, sir. It's gone.
No? Okay, okay, because I think I saw my Zoom's restart. Okay, okay. Because I also make this. I also have a draft of this. Okay, and I saw that it could be changed something because otherwise I told in my case I take also the wrong answers because if I denoted this form, then we can maybe we do not have. I told you that here, say for example, in here, okay, because here we got C1 up to Cn. Okay, so we have NC because we have X is N of X. Okay, and also here we got also the ends of X here. We can multi-use one. So in this case, I think that something should be changed. I think because if we this form, it may not work. Okay. So I think that in this form, I should change this like this. This is because I got wrong answers in my case. So we have this is should be C1, and this should be C2, and this should be C3, and this should be C4, C5, up to Cn. Okay, because when I apply all of these C1s here, C1 here, C1 here, I got wrong answers. Okay. So we have, I think that it should be like this, C1, C2, and C3. Okay, not C1 repeated. Even you see P here is repeat. Okay, and repeat here. Okay.
Okay, sir.
Okay, and because this is I will check with this, but because we have all of x1, x2, and x1, so this should be 1. I will check. Okay, I'm not sure. Yes. Okay, I'm not sure. Yes, but I will check. And if we do that, we will see that I got a similar thing like we got here. It looked like we got something like, oh, okay, TS in my solution is should be like okay. So this is maybe you have to check with for me, and I got the result like 4s plus 1 square minus 3s plus 1 and plus 3 s plus 2. Okay, let me check again. I'm not sure. Yes, because it a little bit take time. We can check. We can find this, and if you check this, we got here. We got TS equal 4s plus 2 minus 3s plus 1 s plus 2 plus 3s plus 1 square divided by s1 square s2. Okay, if this correct, so then we will have the correct answer. But as I said, I'm not sure yet. Okay, because in this case, C1 equal C2 equal minus 3, and C3 is 3. Okay, and then we can replace it here, then got the answer. But let me check to be carefully. I will update this line. Okay, sorry about it because I have no time to clear this carefully. And now I'm doing with you, and I see that is something this should be changed. Okay. I will check with other format. It will be okay. Let me see. I'm not sure. I'm checking. Okay, so this is a 4s minus plus 8, 3 s square, 3 square minus 4s minus 6 plus Is that correct or not?
This is not, sir. It's not correct.
Okay, so I will have to check again. Okay, I'm not sure. Yes, because I just replaced because you said if you have put s plus 1 and then we have infinity case, but you have to put s plus 1 square. Okay, so I will update this. Okay, I'm not sure. Yes, and it takes time for this form. Okay, so I will update this and inform you later. Okay, to be correct this example. Okay, because
Okay, sir. Okay.
okay, I don't know how to config this now. Okay, and because the terms of okay, so I will have to check the attendance today, and we will come back to this later. And for the next section, I would like to ask you to I asked you before, related to the mathematical courses like calculus 1 and calculus 2. So if you are still really good in this section, I will skip this or I will go very fast in the eigenvalue and eigenvectors. Okay, if you got it in my slide, you got eigenvalue and eigenvectors there. So we have to learn this a little bit or review this in the mathematical course. I don't know in the maybe in the calculus 1, calculus 2, or calculus 3. We look at the eigenvalue and eigenvectors and what is the definition of this and what is eigenvector and eigenvalues. Okay, but in this course, it's relevant because we have the equivalent between the eigenvalue, eigenvector with the poles. Okay, and it similar to uh, the poles. Okay, so the eigenvalues and the pole is the same. Okay, but we can prove this in this course because it and again because it's related to eigenvalues, so have to review of this first. Okay.
Yes,
Any
sir.
question?
Yes.
Any more question, please?
Sir, so how about the deadline of the homework?
Okay, let me check attendance today. Okay, 1 week. This I show you the I give you homework and I put also the deadline in the e-learning website. Okay, if you go late, then I will know, and I only extended it to the I'm not sure where maybe in Wednesday next Wednesday.
Next Wednesday, sir.
Are you hear me? You hear me?
Yes sir.
Yes, sir.
Okay, good. I just have problem with Zooms. Okay. So, Bùi Thái Anh.
I'm here.
No? Okay. Nguyễn Quang Anh.
Yes.
Okay. Phạm Tuấn Anh.
Yes.
Văn Đức Chiến.
I'm here.
Phạm Bá Cương. No?
Có mấy em chậm.
Nguyễn Việt Cường.
Yes.
Tạ Mạnh Cường.
Yes, sir.
Đặng Thùy Dương.
Yes.
Lê Quang Đạt. Yes or no? Lê Quang Đạt. Okay. Đỗ Văn Đức.
Yes. I'm here.
Nguyễn Thế Đức.
Yes, sir.
Nguyễn Văn Hà. Vũ Thanh Hải.
Yes.
Đặng Thị Minh Hiền.
Yes sir.
Nguyễn Thị Thu Hiền.
Yes.
Phan Phúc Hiếu.
Yes,
Phan Phúc Hiếu. Okay.
Yes, sir.
Hoàng Văn Hiếu.
Yes.
Lương Công Hiếu. Đó. Okay, Lương Công Hiếu. Again.
Yes.
Lương Công Hiếu.
Yes.
Are you here?
I'm here.
I didn't see you.
I'm here.
Okay. Sorry. Phan Trung Hiếu.
Yes, sir.
Trần Đức Hiếu.
I'm here, sir. Yes, sir.
Vũ Văn Hoàng.
Yes, I'm here.
Đỗ Quang Huy.
Yes, sir.
Nguyễn Quang Huy.
Yes, sir.
Nguyễn Xuân Huy.
Yes, sir.
Lương Văn Huy.
Yes, sir.
Nguyễn Nam Hưng. No. Nguyễn Văn Hưng.
Yes, sir.
Okay. Hoàng Thị Hương. Yes or no? Hoàng Thị Hương. No. Trần Quang Khánh. Trần Quang Khánh, yes, okay. Nguyễn Tùng Lâm.
Yes.
Okay. Nguyễn Bá Liêm. Nguyễn Bá Liêm. Nguyễn Bá Liêm. Okay. But you are not here. Nguyễn Bá Liêm, please. I show you here, but you're not here. Not there.
He's making wrong.
Okay.
He just checks on the box.
Okay, okay. Trần Văn Linh. Okay, one more time, Nguyễn Lam Hưng. Okay, no. Okay, so I think that we got 57 or 56. So I think that I checked Nguyễn Nam Hưng and Hoàng Thị Hương is not here, so other people here. Okay.
Maybe Lương Công Hiếu.
Lương Công Hiếu. Okay.
Yes, sir. Don't check me. Lương Công Hiếu.
Lương Công Hiếu here.
You haven't checked my name.
Me, sir. You don't check me. My name is.
Okay, I know this. This is okay. Now again, Trần Văn Linh, Trần Quang Long.
I'm here.
Vũ Đình Luyện.
Yes, sir.
Đâu Đức Mạnh.
I'm here.
Trần Tuấn Minh. Trần Tuấn Minh. Yes or not? No. Nguyễn Văn Nam.
Yes, sir. Sir.
Nguyễn Thị Nhung.
Yes sir.
Dương Văn Phương.
Yes, sir.
Quách Văn Quang.
Yes, sir.
Nguyễn Thanh Quỳnh,
Yes, sir.
Dương Thanh Sơn,
Yes.
Nguyễn Anh Sơn,
I'm here.
Nguyễn Thái Sơn,
I'm here.
ok, Nguyễn Trần Sơn,
Yes, sir.
Quách Giang Sơn,
Yes, sir.
ok, Hà Tiến Thắng, Hà Tiến Thắng,
Yes.
ok, Nguyễn Hữu Thắng,
Yes.
Nguyễn Ngọc Thiệu, ok, I saw.
Yes, sir.
Nguyễn Văn Toàn, Tạ Thu Trang,
Yes.
Hoàng Mai Trung,
I'm here.
Đào Anh Tuân,
Yes, sir.
Đặng Đình Tuấn,
Yes, I'm here.
Trương Đình Tuấn,
I'm here.
Hoàng Thanh Tùng,
Yes, sir.
Tường Duy Tùng. No?
Yes.
Tường Duy Tùng. Ok. Lưu Thị Hồng Tuyết,
Yes, sir.
Hương Quang Việt.
Yes, sir.
Okay, thank you very much. I stop here. See you again.
Goodbye, sir.
Goodbye, sir.
See you later.
Later.
Bye, sir.
Goodbye, sir. Have a nice day.
Thank you.